Hey guys, it's Mr. Canistero here. In today's video, we're going to go over two questions from the problem set, particularly question 12 and 13, the last two on the back page. I'm making this video because there were a few typos with the answer key, and these questions were difficult enough to where it warranted just a nice review video to go over the steps of the solution. So here we go. Here's question 12. We have two pendulums, a small one, A and B. B has twice the mass of A. So as we're solving this problem, we're going to have to solve it in a few steps. The first step we have to consider, which I'll write as step one, is we're going to do the potential energy, gravitational potential energy of A, use that to find the kinetic energy just before pendulum A strikes B. The purpose is that allows us to find the speed at which it strikes it. Step two of this problem is this is going to be an inelastic collision. So we're going to use momentum, and our goal from that is to figure out the speed that both pendulums move together as they fly off. Once we know the speed, then we can use energy once again. In this case, it's a kinetic energy to gravitational potential energy conversion to go back and solve for how high the pendulum system rises to. One quick reminder, if mass B has twice the mass A, we're just going to rate that this is 2m of A, so we can just keep track of it. All right, let's go through and we'll start this problem. So first off is step one, the potential energy to kinetic energy conversion. So this pendulum starts half a meter up in the air. So we can use gravitational potential energy. So mg, in this case, h is 0.5, equals 1/2 mv squared. And so performing the math and solving, we get the following. After math is performed, we get the velocity upon impacting is the square root of g, or about the square root of 9.81, and that gives us the speed. I'm just going to leave it as the square root of g. Now, for part two of this problem, we know this is an inelastic collision. So also we know that pendulum B is standing still beforehand, so it has no momentum. So we're going to use the conservation momentum. The momentum before a collision equals the momentum after a collision. So what we have here is the mass of A times the velocity of A equals the mass of A plus B, because they stick together, times the velocity that they move back off at. Therefore, the velocity then is simply going to be the velocity of A divided by, the velocity of A times the mass of A. Let's try to scooch that over. I'll just rewrite it. Divided by the mass of A plus the mass of B. Now, because the mass of B is twice the mass of A, we can rewrite this whole bottom statement as 3 times the mass of A, leaving us the masses cancel out, and so it's the velocity of A divided by 3. So in other words, when they hit and stick together, the resultant velocity is the velocity cut into a third, or in other words, because our velocity was root gravity, it's root gravity divided by 3. So now we know the speed that this pendulum system moves off at after the collision. So finally, for step 3, I'm going to go over here to the left, we can use conservation of energy once again to figure out how high it rises up to. And so again, we're setting kinetic energy equal to potential energy, so we use our equations, half mass velocity squared. In this case, the mass is A plus B, so it's both masses together, equaling mgh. And again, it's both objects, A and B, when we're talking about our masses. Regardless, it doesn't matter. The masses cancel out. Again, when an object's going up in the air and gravity's decelerating it, gravity doesn't care what the mass is. And so solving for h, we get that h is v squared divided by 2g. Recall that our velocity was the square root of gravity divided by 3. So that becomes squared, and we divide by 2 times gravity. So when it's all said and done, you perform the math. The square root of gravity cancels out with the gravity. The 1/3 squared becomes a 9th, and so we end up getting 1/18 of a meter, or that comes out to be 0.056 meters. And that is how high up the system rises to. So that is it for number 12. All right, I'm going to take a brief second to pause. You go ahead and finish copying this down, and we'll start with number 13 in just a minute. All right, we're back. I've enjoyed a nice 5-minute break. Looks like it's been about 2 seconds out there in YouTube land. We're now ready to start number 13. So number 13 is your two-dimensional collision problem. This is two curling stones. So in this problem, they collide elastically, as shown in the picture. Using the information provided, we're going to figure out the speed and angle that stone D moves off at after the collision. So let's just take a minute to dissect this problem, see what we have, and then we'll go from there. So note in this collision, before the collision, we have mass C given as 10 kilogram as the mass, moving at 12 meters per second, that's its velocity, moving entirely in the x-axis direction. It strikes object D, and then after the collision, object D moves off at some unknown velocity and unknown angle, but we are told that object C is given at a velocity of 3 meters per second at an angle of 60 degrees. So for this problem, what I'm going to do is I'm going to use red marker to denote any momentum or calculations in the x direction, and I'll try to use blue marker for any momentum or directions in the y direction. All right, so let's get started. So first, we're going to analyze in the x direction. We know that momentum is always conserved, so momentum before a collision has to equal the total momentum after a collision. Now, this is true both in the x and in the y direction separately. So what that means then is, if I rewrite this, the momentum in the x direction before the collision, so x before, has to equal the momentum in the x direction after the collision, and then similarly for the y direction as well. So in the x direction, we're starting out with a mass of 10 and a velocity of 12, and d is at rest, which is a momentum of 0. So our total momentum then before the collision in the x direction is 120 kilogram meters per second. That must be the total momentum in the x direction after the collision. So that means this must equal the mass of d, which is 10 kilograms, times the x component of the velocity of d, plus the mass of c, times the x component of the velocity of c, which we can find that using trig. It's pretty simple. If this is 3 meters per second at an angle of 60 degrees, the x component is just the 3 cosine 60, which is half, 1.5 meters per second. So solving for this first part becomes pretty straightforward. If we have 120 on one side, we know that the mass of D is 10 kilograms, and we're trying to solve for the velocity of D. We also know that the mass of C is 10 kilograms and its velocity is 1.5. It becomes a straightforward math problem to then show that the velocity of D in the x direction, we subtract over by the 15 and then divide by the 10, you end up getting, 1.5 meters per second. Sorry about that. You end up getting 10.5 meters per second in the x direction. So if we go back to our picture then, that means in the x direction, this object is moving, object D is moving at a velocity Vx of 10.5 meters per second. So now we need to talk about what's happening in the y direction. So in the y direction, we're starting out with a momentum of 0, because the reason is all the velocity is directed in the x direction. That means after the collision, the total momentum has to be 0. Or in other words, the mass, actually I'll scroll down so it's a little bit nicer. Let's just go ahead. Oh, flying away on me. So in other words, what we have here is, again, the momentum in the y direction before the collision has to equal the momentum in the y direction after the collision. Because it's 0 before, it has to equal 0 after, meaning 0 has to equal the mass of C times the velocity of C in the y direction, plus the mass of D times the velocity of D in the y direction. Or in other words, the two have to be equal to each other, just opposite in direction. So I'll write it as the mass of C times the velocity of C in the y direction has to equal minus the mass of D times the velocity of D in the y direction. So, performing the math then, what we have is the mass of C is 10 kilograms. The velocity of C in the y direction can be found, again, by doing some basic trigonometry. If we look at it, this is the y component of the 3 meters per second, so it's 3 times the sine, I'll write it down, the velocity of y, the velocity of C in the y direction is 3 times the sine of 60 degrees, which comes out to be about 2.6 meters per second. So putting down here, the velocity of C in the y direction is 2.6 meters per second. Clearly, because object D has the same mass, then its mass is 10 kilograms. It also has to be moving at 2.6 meters per second. And so we finally have the velocity of D in the y direction is 2.6 meters per second. So to get our answer then, let's look at the two velocities we found. We said that in the x direction, it's moving at 10.5 meters per second. In the y direction, it's moving at 2.6 meters per second. And so the resultant velocity and angle can then be found by using Pythagorean's theorem and by using basic trigonometry. Because I'm running out of time, people are walking in my class, we get the resultant velocity is the square root of the sum of the squares. You end up getting 10.8 meters per second at an angle of, the survey says, 13.9 degrees. And there's the solution to the problem. Hey, happy holidays, everybody. Hope you guys have a great break, and best of luck with the rest of the problem set. Remember, if you have any questions, feel free to contact me on Remind. Hasta luego.